All right, welcome to Physics Video 8.2. We're going to learn about the basics of sound waves. All right, I'm not listing the objectives here because it's basically just a bunch of definitions and stuff. So you need to know the definitions and stuff. All right, so here we go. A sound wave is caused by a vibrating source. The idea is the vibrations from the source are going to cause the medium, the particles of the medium that it's in to vibrate. Those vibrations are going to emanate outward from the source in concentric circles, similar to if you dropped a rock into a pond, you would see the ripples spreading outwards in circles. As the vibrations move, they could eventually reach your ears. Those vibrations will cause your eardrums to vibrate, and your brain interprets that as sound. All right. As we're going to see here in a second, it turns out that sound is a longitudinal wave, which means that if the energy is traveling this way, your particles are going to go back and forth in a direction that's parallel to that. All right. So let me show you an example of this. All right, so what we've got here is a faucet. The faucet is dripping water. So the drips of water represent the vibrating source that causes the water to vibrate. And while there are sound waves here, that's not what we're looking at here. We're looking at just regular water waves. But what I want you to understand is that in the same way that the vibrating water causes the water to vibrate, the vibrating source can cause your sound waves. All right. So here we've got a little speaker that is vibrating back and forth like this, right? You can see the kind of grayscale where it goes from light to dark. The dark parts represent compressions of air molecules. The lighter parts represent the rarefactions, where the particles are farther apart. If it helps, if we jump back to the water example, we can see the same thing if we just rotate this. Right now we're looking at the water from a side view. If we rotate it, we can look at it from top view and see a pattern that looks almost the same, right? So this is cool, but we can't see the particles. So let's click on this so we can see the particles. All right, and here you can see the particles vibrating back and forth. All right, so that's what the source of our sound wave is we've got this cone over here. The cone vibrates back and forth, causes the air molecules to vibrate. You can see you get these concentric circles kind of rippling outwards, like if you drop a rock into a pond, and there we have our sound waves. All right, so we will learn more about sort of the properties of that wave here in a minute, but I did want to show you just sort of how the waves are created first. All right, so more about the wave itself. As is the case with any other wave, the velocity of the wave is going to be determined by the medium that it travels through. This chart here is actually at the top of your next homework assignment, but it just shows you for different mediums that the air is traveling, or that the sound is traveling through. It shows you the velocity. Okay. Couple things worth pointing out. In general, the denser the medium is, the faster sound travels, right? Gases seem to have the smallest velocities. Liquids are, in general, larger, and then in general, the solids are even bigger than those. And then another generalization is this. As a general rule, the warmer your medium is, the faster sound travels through it. Okay? Because if it's warmer, it means the molecules are vibrating faster, they have more kinetic energy, and it causes the sound to travel through faster. Okay? So this actually brings us to an interesting result, and I'll talk about this more in class, I'm guessing, because somebody will ask about it undoubtedly, but sound actually travels very, very quickly through solids. But that doesn't mean that it travels easily. It means that if you have enough energy to get, iron to vibrate, to carry a sound through it, it goes very, very quickly. But because the bonds holding solids together are so strong, it actually loses its energy very, very quickly. All right, so the velocity of a wave is determined by the medium it travels through. All right, now the pitch of a sound is determined by the frequency of the vibrations. All right, in other words, the higher the pitch is, the higher the frequency is. So if you think about, like Chef on South Park, where he says, "Hello, children," in a very deep voice, that would be a real low frequency. And then one of the kids on South Park, would be higher pitch like this. Okay, and so that would be a higher frequency. All right. In general, humans can hear sounds between about 20 and 20,000 hertz. A sound that's higher than 20,000 hertz is called ultrasonic, and if it's below 20 hertz, it's called infrasonic. All right. And then two other words that are not related but are important anyway are supersonic and subsonic. Those don't have anything to do with the sound wave itself. They have to do with an object. So an object is called supersonic if it's going faster than the speed of sound. and it's subsonic if it's going slower than the speed of sound. Okay, so it would not make sense to say, oh, that wave is supersonic. You could say, oh, that jet is supersonic, or that bullet is supersonic, because it's an object moving faster than the speed of sound. Okay. Cool. Right, the volume of a sound wave. We talked about the pitch, right? The volume of a sound wave is determined by the amplitude of the vibrations. The louder the sound is, the bigger the amplitude is. All right. There are two different ways that we can measure the amplitude of a wave, or measure the volume of a wave. The first way is in what's called intensity. All right. The intensity of a wave is a measure of how much power it puts out per square meter. So if you notice, I kind of created this chart here where there's intensity, decibel level. You can convert from intensity level to decibel level. There are different ways of measuring the same thing using logarithms, which we don't care about. And then I gave you an example for each one. So I sort of pieced these together from different books and gave an example of each. All right. So let's look at this. So let's look at, for example, an air conditioner at 6 meters. So suppose you're standing outside by your air conditioning unit and you're about 6 meters away from it. All right, what that means is the intensity of the sound that you're going to hear, the amount of power it carries per square meter, is 1 times 10 to the negative 6th watts per square meter. That can be converted into what's called decibel level, and you get 60 decibels. Okay? So the next example on here is a vacuum cleaner. So if you're running a vacuum cleaner, then the intensity level is 10 to the negative 5th watts per square meter. So notice it got 10 times louder, right? But the decibel level got 10 bigger, plus 10. So in other words, the intensity level, it increases by multiplying, sort of, and your decibel level is increasing by adding 10. Okay? So suppose that you were, I don't know, listening to, you guys are all big Justin Bieber fans, right? So you're listening to Justin Bieber at this level, all right? And then you're like, whoa, this song's my jam, and you turn it up. I can't even name a Justin Bieber song. I should have picked something else. But so you turn it up to this level, all right? So what happened is you turned it up from 10 to the negative 8th up to 10 to the negative 5th. So you turned it up 1,000 times louder, right? You multiplied it by 10, 1, 2, 3 times. So that's 10 to the 3rd times louder, right? But notice the decibel level, you added 10 to it 3 times, right? So overall, you added 30 decibels. Okay. So the decibel level, as you get louder, you're sort of adding decibels, and with intensity, you're sort of multiplying. Okay. There's more to it than that. The main reason this is happening is because this is a logarithmic scale. But I don't want to get too bogged down with the math. All right. So you should be able to do stuff like this. Like suppose you heard a sound at 90 decibels and then you turned it up to 110 decibels. If I asked you how many times louder that was, well, you added 10 twice, right? You increased by 20 decibels. So that means that you're multiplying by 10 twice over here. So it's actually 100 times louder. Okay. So we'll talk about that more in class. That's really one of those things that I think we're going to have to sit down and look at on paper. Okay. So if you understand one thing, there are 2 things you absolutely must understand leaving here. One is there's 2 ways to measure volume, by intensity or decibel level, and 2 is as either of those things go up, it means your volume is going up. Okay. All right. Now, the intensity, the volume of a sound, varies inversely with the square of the distance from the source. All right. In English, what that means is the farther away you are from a sound, the less loud it seems to be. All right. So going back to that air conditioning unit, if you're 6 meters away from it, then the intensity is that, right? Now, it's an inverse square relationship. So what that means is if your distance gets multiplied by something, then your intensity, I, is going to get divided by the same number squared. Inverse square. Okay, if your distance gets divided, then your intensity gets multiplied. Okay, so in this first example over here, our distance went from 6 down to 2. So the distance got divided by 3. That means my intensity is going to get multiplied by 3 squared. So I would take my original intensity of 1 times 10 to the negative 6th watts per square meter. and then I'm going to multiply it by 9, right? 3 squared. So I'm going to get an intensity of 9 times 10 to the negative 6th watts per square meter. Okay? And then in this bottom example, now the distance went from 6 up to 12. So now the distance is getting multiplied by 2, which means my intensity is going to get divided by 2 squared. So I'm going to take 1 times 10 to the negative 6th watts per square meter. I'm going to divide it by 4 to get 2.5 times 10 to the negative 7th watts per square meter. Okay? So, that's the deal with intensity. All right, I'm probably saying this too late, but the numbers on this chart you don't need to copy down. They will be on your next homework assignment. I hope you didn't write them down already. I apologize if you did. Okay, so the last thing then that I wanted to do is show you this graphic again and show you, well, let me do this. First of all, I can show the graph here. When you show the graph, what it's showing is the pressure at certain points. So like, for example, if I pause it, right here you can see the air particles are really close together. So if you, to increase pressure, that means you want to smoosh your air particles close together, right? And so notice that this high pressure here corresponds with a higher pressure on my graph. Okay? So watch what happens. I'm going to change the frequency. So right now, if you look over here at the side, the frequency is pretty low, right? So let's increase the frequency. As the frequency goes up, the wavelength should go down, right? So now you can see the waves are much closer together, right? Now the wavelength is from here to here-ish, something like that. Okay? If I increase my frequency even more, the wavelength gets even smaller. Cool. You can see that the pressure decreases as you get farther away. You're losing energy. Okay. Unfortunately, the drawing here, you really can't even see what's going on because the compressions and rarefactions are so close together you can't even distinguish between them. If we switch to grayscale, you can see a little bit better. Okay. So let me decrease my frequency and you'll be able to see the waves get longer, right? Okay, and then the amplitude is just going to affect the volume of the sound. So that would be a loud sound, and this would be a smaller, quieter sound. All right, I'm going to turn on the sound here for 1 second just so you can hear them. I hope Miss Lanning does not freak out since she's teaching next door while I'm doing this. So here we go, sound. Oh, maybe I won't turn it on. Why is the audio not working? Oh, because I turned off the speakers. Okay, so there we go. So right now we're at a low frequency. So what I'm going to do is increase the frequency. Right, higher frequency. Higher frequency. Unfortunately, I don't think changing the amplitude will change the volume. Oh, it does, look at that. Okay, notice right now I'm just changing how loud the sound is. I'm not changing the frequency at all. Okay, so you can have a low frequency at a high volume, or a high volume and a high frequency, or whatever. All right. Okay, so there we go. Sound waves. I think we're done.